Do we live in a simulation? Earlier this year, we finally got a definitive answer. So, how can we know for sure? Stick around and find out. Simulation theory has been around for a while, but it's been most popular in the past decade or so as computing power has grown. The earliest form of simulation theory, though, was Plato's allegory of the cave. Basically, Plato said that life is like being a prisoner in a cave, and all we can see are shadows on the wall. Since all we can see are the shadows, that's what we think is real. But if one of the prisoners were able to escape and see the outside world, he would see that there's so much more than just the shadows. He would see the real things that are casting the shadows and be able to understand reality a little bit better. Modern simulation theory is pretty much the same thing. The main difference here is just that we're stuck in a computer, not a cave. But if we were able to leave this computer, then we'd be able to experience real reality. We would be able to see things how they are and not just how they're presented to us. The big problem here is that to run a simulation like that would actually be pretty hard. The computer would need to be able to simulate every atom everywhere in the universe and how they're all affecting each other and interacting with each other, including gravity and electromagnetic forces. For a full resolution simulation, it would have to calculate things on a 1-to-1 scale, meaning that it would only have 1 second to calculate everything that happens in 1 second. But it would have to calculate those at the Planck length. The Planck length is just the shortest that something can possibly be. Think of it as the pixel of the universe. There's also Planck time and Planck mass as well, but we don't really need to get into that for the sake of this video. The main point here is that if we wanted to do a perfect full resolution simulation of the universe, everything would have to be calculated on a really small scale. The amount of energy and resources to build and run this computer would probably be almost everything in the universe. So it would take the whole universe to accurately simulate the whole universe. But what if we cut a few corners here? There are some tricks that we can pull from modern games that make simulation a little less resource intensive. The first thing we would want to try is turning down the render distance. If something is so far away in a video game that you wouldn't really be able to see it, or it would just show up as a single pixel on your screen, it oftentimes just won't render. You don't need to load something that you can't see. No need to waste computing power on it. Another trick would be to lower the resolution of faraway objects. Oftentimes in games, if something's really far away, either the visual resolution will drop or its frame rate will drop. Game designers will again do this to save on computing power. And if it's far enough away, players won't really notice or be able to tell. So if our universe is a simulation, then that's another way that whoever made it could save on computing power. There are a few other tricks that modern games use, but I think you get the idea. So whoever made the simulation would be able to use these techniques to greatly reduce how much energy the universe simulation would take to run. The only thing that would need to be at full resolution would be things that we're looking really closely at. You wouldn't need to simulate every single atom, just the general function of things. And we actually kind of see this happening. With studies like the dual slit experiment, we've actually seen that things do behave differently when we're looking closely at them. Some have said that this is the best evidence yet that we're in a simulation, but the more we've studied it, the more that we've seen that quantum things are just weird. We don't really need to get too much into what the dual slit experiment was right now, but if you do want to learn more, there are a ton of videos out there about it. Anyway, with all of these things considered, simulation theory got more popular than ever. In fact, a lot of people, including some scientists, have said that it seems more likely than not that we're in a simulation. A lot of people pointed out that this could also solve the Fermi paradox as well. Whoever made the simulation only cared about us, so didn't bother adding aliens. A very human-centric view of things, certainly, but it made a lot of sense to a lot of people. Anyway, fast forward to earlier this year. Simulation theory has been proven wrong. A paper came out saying that our universe being a simulation is actually impossible. How do they know? There are a few things that being in a simulation just can't explain. The basic building blocks of a simulation is algorithms, and there are certain things in the universe that algorithms don't work on. Here's a quote from the paper. Purely algorithmic deduction is therefore insufficient for a complete foundational account. These things can't be explained with math, therefore, we can't be in a computer. So, yeah, problem solved. QED, pack up, we're done here. But there's actually something else we should consider. John Wheeler's It's from Bits perspective of reality. John Wheeler was the inventor of black holes and explosions. Okay, maybe I'm being a little hyperbolic. He did coin the term black hole, though, and he did work on the Manhattan Project, which is to say that he was a brilliant physicist. He also did all this other stuff, too. So, yeah, bro knew science. Anyway, his It's from Bits theory basically says that everything in the universe can be described by bits. Well, more accurately, qubits or quantum bits, but the word qubit wasn't really around when he came up with this theory. It's what he meant, though. So It's from Bits means that everything in the universe can be described with qubits, and so the entirety of physics is just computer science. Quantum computer science, not the normal stuff. In normal computer science, a bit is either a 1 or a 0, but in a quantum computer, it can kind of be both. Long story short, this just means that a quantum computer can calculate things a lot faster and a lot more efficiently. But is the universe really a quantum computer? Well, it's actually looking more and more like that every day. Quantum physics is really weird, and it looks like most things can actually be explained with qubits. So really, the universe isn't made up of energy and matter. It's made up of information that then defines the energy and matter. We get the its, energy and matter, from the bits, or qubits, as it turns out. So what does that mean for the nature of reality? Well, it's not that we're trapped in a computer, it's that we actually are the computer. We as humans and the universe as a whole are just manifestations of a super complicated problem. The universe as a whole is doing one big quantum calculation. So I guess Douglas Adams was kind of right. Even the authors of this paper say that their idea kind of lines up with the It's from Bits ideology. These insights resonate with Wheeler's It's from Bits program and its modern version in both string theory and loop quantum gravity, which propose that information is more fundamental than physical reality consisting of space-time and quantum fields to define it. But this doesn't necessarily mean we're in a computer. Think about it this way. I can say a plant is 42 inches tall, but it doesn't mean that the plant is made of 42 or measurements or math. We can say a plant is green, 42 inches tall, made of cells, or any other way we want to describe it, but the reality of the plant is a lot more complicated. And that's true with the universe too. Our analysis instead suggests that genuine physical reality embeds non-computational content that cannot be instantiated on a Turing equivalent device. Since it's impossible to simulate a complete and consistent universe, our universe is definitely not a simulation. There are things about the universe that can't be quantified with computers, not even quantum computers. By the way, quantum computers basically just do the same kinds of things as normal computers, but at a much faster rate. To summarize the paper, there are things like Gödel's incompleteness theorems that show that we don't and will never have a full understanding of math. There's no complete and consistent set of axioms that can apply to all of math, and math is the base of physics, so there's no complete and consistent set of axioms to describe all of physics. To put it simply, math will never be enough to explain everything. There's a lot of other complicated stuff in the paper that I left out, but the paper ends with this. The arguments presented here suggest that neither its nor bits may be sufficient to describe reality. Rather, a deeper description, expressed not in terms of information, but in terms of non-algorithmic understanding, is required for a complete, consistent theory of everything. The universe cannot be explained by math alone. Therefore, we know we're not in a simulation, because a simulation would be 100% based in math and algorithms. We are in a real reality. It seems to me that most people who are really into simulation theory want there to be a higher power, but don't want that higher power to be God. And fair enough, a lot of people have done some pretty bad things in God's name. But those who support simulation theory want to think that someone is in charge. Well, I have some good news and some bad news. You're the one in charge. We collectively and individually have that power, and it's our responsibility to use that power for good. We shape the universe, and the universe shapes us. Anyway, have a wonderful day, and remember to stay curious.